Assalamualaikum and good day everyone. So today is we will going to cover week 8 lecture. Okay, so now is 4 of May 2021 and the time here is 1:40 a.m. Okay, let's see how long I will finish. Okay, but I hope you guys bear with me. I know the lecture sometimes is long, but you know it's better longer than shorter, right? If shorter, maybe student will complain I didn't teach much, or maybe I don't cover so much. But you see, actually EMT, there's so much thing to cover, okay? And some it's possible that it's not able to cover all. So that's why I share to you guys the lecture from other videos, okay? You see the other lecture also, maybe they don't cover everything as well, okay? But so please always read the slides and also read the Sadiko. Sadiko will have more detailed informations, okay? So in week 8, okay, now we are in week 8, okay? So we will study about Imperial Law, okay? To obtain our magnetic field intensity for symmetric current distribution, okay? I will detail later on, okay? This one just to give you overview so that you clear what should be learned in week 8, okay? And then after that, the introduction, to curl concept, stock, theorem, and magnetic flux, density, okay? So this one you can actually get from your course information, okay? From your week 1 slide, okay? I think I shared this before. Okay, just before we proceed with Imperial Law, let me refresh first what we have been learned in the previous week 7, okay? So previous week 7, we actually learned about Biosafety Law, okay? This one is from your Sadiko book, page 292. Okay, from page 292, okay? So we learned about Biosafety Law. So Biosafety Law is actually just like a repetition or analogous to Coulomb's law, okay? Means the way we solve in order to obtain H, the magnetic field intensity, is more complicated, more cumbersome compared to the what that we're going to learn later on, which is Imperial Law. So this is analogous to Coulomb's force, and you guys can see as I write the table of comparison here, okay, with electric, magnetics, okay? You find some similarity there, okay? It's for example like this one, okay? You can see here we have permittivity, here we don't have, okay? And instead is this electricity involved with charge, we are involved with current, okay? And here is cross products, okay? So then you learn about in the previous class actually the equations of having to get the differential or small variation of magnetic field intensity, and you come across this equation, okay? And I also introduce you guys to this concept, okay? Right hand rule, and also we need to see sometimes of the way we imagine things, okay? Like this is screw, right? If you have dot, dot, and X is different. If you have dot, means it is coming out of the paper, okay? Coming out. And if you have this one, it means going inside the paper, okay? Can see this, right? Okay, so after that you also learn about in the week 7 you learn about the variation of H equation according to your source of current, line current, surface current, and volume current. Just a change here, okay? IDL, KDS, and JDV, okay? And also similarly, like you have these kind of things inside this kind of situation inside the Coulomb's law, okay, you also have this here, but instead of charges you are solving with regards to current, okay. And then you'll also learn about this if it's infinite in length, okay, simplified this one, where this one alpha 1 and alpha 2 will become 90 degrees, then you will have this general represent equation, okay. So now without further ado, we go to the Ampere circuit law, okay. Ampere circuit law. So here stated the Ampere circuit law stated the line integral of H around a closed path, okay. You see, around a closed path, this is important point, is the same as the net current I enclosed by the path, okay. Actually, Ampere circuit law is an alternative to Biosafety law, means it is simpler solution. I mean, simpler way to solving to obtain our H and so on, okay, to obtain our magnetic field intensity and so on. Just like Gauss law is a simpler way of obtaining your force, your electric field intensity and so on, compared to Coulomb's law. However, just like Gauss law, Ampere circuit law also have condition for it to be valid, okay. So for it to be valid is one of that is that this Ampere circuit law is applicable to infinite current source, okay, whether it's line, surface or volume. And why we need to have this infinite current source, just like the same as Gauss law, because you want to have symmetrical distribution, okay. In Gauss law we want to have symmetrical charge distribution, right? And similarly but not indirectly the same as in Ampere circuit law, we want to have a symmetrical, okay, where the current distribution is symmetrical, then only then we can use Ampere law, okay, Ampere circuit law. So please, that's why this one is important, okay. Don't just read definition, you must also understand what have been written here, because this Ampere circuit law, just like Gauss law, it is not always valid to be used, okay. Means that when you want to use Ampere circuit law or Gauss law, you need to make an assumption, okay. Sometimes in equation you need to make assumption to solve the equation, to solve its problem. We will not directly tell you solve this using Gauss law or solve this using Ampere circuit law and so on, okay. You need to decide. And also, just like uniqueness theorem, whether it is Poisson equation or Laplace equation, which one, okay. So this Laplace, and for Laplace and Poisson is main differentiation is the rho v, right? If rho v is 0, is you solve using what equation, okay, you guess yourself. And if it's rho v having value, you solve using what, is it Poisson or Laplace, okay. So I'm referring to various sources now, if you in to that, so that I hope that I can cover as much as possible. Sorry for this lecture. So there will be sometimes I talk from the slides, sometimes I talk from Sadiku, okay, and then sometimes I talk from any other source, okay. So okay, this is you see the equations, okay. Now we put this one away later on, okay, but you just need to know that for this to be valid, okay, it is this one is alternative to Biosafety, applicable to infinite current source, okay, like this, infinite line current, infinite sheet current, okay, infinite long coaxial transmission line. Remember in the past test and some examination, we need to, if it's infinite, we for the electrostatic, we can solve using Gauss law because it is infinite, okay. Because when it's finite, the charge distribution is symmetrical, okay. So sorry for that. Okay, this clip sometimes make my life a bit difficult, okay. So we put this away, okay, we put this away first, okay. So what we in Ampere circuit law, okay, Ampere circuit law, we have closed integral, okay. What does it mean, closed integral? You guys know? Because it's a closed path, okay. same as the net current close. Okay, we need to have enclosed, means this is no open loop. Okay, so then we have hash, okay, dot dl vector, then you have I enclosed. Okay, okay, so the way we solve using the way we're going to solve using Ampere's second law, okay, first, as usual, we need to know what coordinates that will be used. Is it Cartesian? Is it cylindrical? Or is it spherical? Okay, so this is important. Second step is that we need to determine where is our location hash. Okay, where is the sampling point where we sample. Okay, and the three, we need to have Imperial loop. Imperial loop is actually the loop, the closed loop. Okay, the closed loop that we will make this sampling. For example, if you have current here, okay, moving here, okay, so your Imperial loop, okay, like this, okay, going like that. So your Imperial loop, you can understand. So this is your loop, but it is must be closed. Okay, and then then you start solve the equation accordingly. Okay, as problem accordingly using this equation. Okay, sorry, I need to find some equation to share with the class. Okay, to share with the class. Okay, so I didn't find from Sadiku. You guys can find later on. Okay, but I know that equation exists, but I just didn't find the page. Okay, so and then when this one okay, actually we can extend it some more. Okay, so if you have hash dl, okay, equals to I enclosed, am I correct? Okay, and then this one is actually the total current inside the closed loop, the total current inside here. Okay, we have this our closed loop, but what is the total current inside here? So this means that this one is also can be extended, that this is a JS DL. Okay, you guys can try to find from the Sadiku book and also from the slide. Okay, this equation I didn't seems to find them right now. Okay, actually of course I can. Okay, I think I find it, never mind. Okay, so JSDL, and also you can also extend it to be J.ds. Okay, so I hope this is here. This is double integral. This is single integral because it's on both line. This is in both surface. Okay. So just like this one, if I zoom it out, okay, so and just to make you guys know, in EMT, okay, sometimes we will have zoom in view. Okay, sometimes we have zoom in view and we have zoom out view. Okay, depending of which zoom in or zoom out, we will have different way of solving it. Okay, but for now, let me go first. Okay, for let's say for the Imperial loop, I make this one bigger a bit. Okay, so let's say we have an infinite current. Okay, this is your, for example, this is your current. Okay, then you have that closed loop. Okay, you have that closed loop, and then you have some sampling of DL. Okay, and this is your closed loop. So this is your radius. Oh, I forget, I have a lot of color. Okay, so this is your radius. Okay, so this is your different sampling. Okay, now this is your closed loop. Okay, so this is your eye, so it means that this is your eye and close. Okay, so okay, like what I told you guys, depending on zooming in or zooming out. Okay, if we zooming out, okay, if we zooming out, this one is if just like a line current. Okay, just like a line current. But if we zoom in, okay, let's say if we wanted to zoom in, this structure will actually become cylinder. Okay, if we zoom in. Okay, if we zoom in this wire, okay, it is become a cylinder then. Understand? Still having the same closed loop, but now instead of having line, it is in fact of only line. Now it is become just like a volume. Okay, so when you solve, okay, let's say this is your RA, correct? Am I correct? This is your, no, let's say this one is your RB, for example, RB. Then this one, you will have two conditions then, RA and RB. Okay, so just like to Gauss law. Okay, just like similar to Gauss law, Imperial circular law is just like Gauss law, means you have region. Okay, you have region because you have closed loop. So here this is the same, so means you will have hash for the R less than A, and also R less than A greater than A, and R for example greater than B. Sorry. Okay, the same. Okay, this is zoom in, this is zoom up, this is zoom in. Depending whatever the term they use, just the same. Okay, let's say they use microscopic or macroscopic, is the same thing. This one is macroscopic view, this one is microscopic view. Okay, so far so good. Okay, so you can see from the slide, they also slide in also Sadiku, okay, for more detail and more information. Okay, because I cannot cover word by word, right? In lecture is not logic. Okay, so if we consider, okay, current, this one to be valid is that symmetric current distribution, so it must be having using infinite current source. Okay, so you can see, of course, this one I forget, even though I already shown just now, but I just, if you, in case you guys forget, okay, it's page 302 on from there and onwards. Okay, so infinite current source, so you can have a line which is infinite. Okay, you can have current, you can have volume. Okay, and you can see later on from the equations, okay, they make simplified because of this infinite. Okay, for example, the line, it is h equals to 1/2 pi r unit direction. Okay, and for infinite surface charge, okay, and then for the volume, if they shown, Oh, I didn't seem to find, but you can read from the book, okay? Where is the volume chart? Volume current. Definition of current. I think this volume is depending on your solution later on situation, okay? I don't know why they don't cover. They should be covering, okay? Okay, I think you can see from the A, B, C, okay? Condition, okay? So now, okay, with the slide, okay, the slide that I already shared to the class, you can see the example, okay? Example, they show some example. How you can try yourself, okay? Maybe they show example and answer to solve it directly. And please, you need to try yourself so that you know that you understand or not, okay? Even though it's good because now the example in the slide or tutorial having giving answers, only the answer, and the slide that I'm sharing is showing, for the example, is showing the stem, so it's good. Okay, just practice, okay? Practice. There is no shortcut with EMT, okay? There's no shortcut. I have to be true to you, okay? And this is what covered by Imperial Law. Later on, we will extend to learn about magnetic flux density, okay? This one later on, okay? The magnetic flux density is B, okay? Is B. But in electrostatic, the electric flux density is D, okay? It's just similar, analogous, okay? So, I don't want to spend so much on the lecture, okay? This is just like so much. This is what you should be learning in for the Imperial Law, okay? It's just, and then it is a repetition of the Gauss law. So make sure that you master your Gauss law properly, because the way we are solving, the way we approach Imperial law is a bit as similar as how we approach Gauss law to solve electrostatic problem. Now we're using Imperial law to solve magnetostatic problems, okay? So so this is the what we should be covered for Imperial law, okay? More or less, okay? So you guys can read detail from the Sadiku and also from the slide, okay? And try the tutorial, okay? Of course, you need to try exercise, okay? It's about these things. It's about mathematics, so there's no really shortcut, okay? So let me see the exercise, okay? Exercise. Okay, let me see for this question practice. 7.5, okay? So it's mentioned that plane Y equals to 1 carries current K equals to 50 AZ milliampere per meter. Find H at this origin and this. So this is your sampling point, okay? And of course you have the answer here. Okay, you see when it mentioned plane Y equals to 1, this means there's no limit. Only Y equals 1 means that we don't know until when actually this surface charge surface current is extending. So this means that this one is what? This simply means that it is a infinite sheet of current, okay? Okay, we put this one away, okay? And then I like to remind everyone again and again, repetitions, okay? It's okay, maybe you get bored, I'm keep on repeating, but it's okay. I want the best for you guys, okay? Always try to have some time, more time, to watch the supplementary video, because this is a collection of video that they have made in the past. Okay, so they have a lot of example, they have a lot of problems, and they provide you solution. So please refer. Okay, as I'm just starting to teach EMT this semester, so logically my video is not much as not much as them. It's logic and their experience, so they cover a lot in shorter time compared to me. Okay, I have to admit. Okay, but it is for good of you guys. Please refer to the supplementary video, and also there's the lecturer, Dr. Nozar. Okay, I shared in the e-learning her lecture as supplementary material 2. Okay, supplement material 2. So okay, let's first we try to, you know, like any of a solution of AMT problems, we try to imagine. Okay, the problem with AMT, you cannot see things, right? So that's why when you cannot see things, you have to actually imagine what is the situation like. So it's mentioned that plane Y carries current K. Okay, first we try to imagine the situation. Okay, so the standard one, X, Y, and Z. Okay, then the question says plane Y carries current K, means at Y1. Okay, and it is always, it doesn't have limit, mean it is a infinite surface charge. So it is actually infinite. Okay, infinite. You can have a big, okay, infinite. And actually, if we zoom in, okay, this thing, this person, I mean this surface charge, actually this is made of a tiny line current. Okay, if you zoom in, okay, just for before we saw the equation, okay, if we zoom in, this one is actually made by a tiny of line current. Okay, and this is your loop, this is your magnetic field. Okay, okay, together. Okay, here, okay, we try to see from this view. Together, this line current, a lot of them, making a surface current. Okay, so you see the arrow. Okay, okay, the direction. Okay, so you will have effective, okay, field. Okay, like this one, you can see the arrow, right? This one is going up, this one is going down. Okay, so I try to see colors. Okay, this one, so this one at this side, it is going this way. Okay, and at the other side, the magnetic field is this way. Okay, because you see from the resultants. Okay, from the resultant, I hope you guys can see it. Okay, so actually surface charge, surface current is made by a tiny line current. Okay, okay, we don't waste more time. Okay, now, and then this is the situation, and then what they say in the practice exercise 7.5. Okay, plane Y carries current of K equals to 50 AZ. Okay, you see, it shows that AZ is unit direction of Z. So, okay, we try to make into what we're familiar with. Okay, don't leave 50 Z. Okay, milliampere per meter. Okay, so this is our current. Okay, so now the question is say find hash at 0, 0, 0 and also 1, 5, 93. Okay, so I just try to cover this. This one is just the same, it's the repetition. Okay, just the way that we need to do the same thing to get the answer. So you see find hash at 0, 0, 0. Okay, if you look into the hash for the surface for infinite sheet of current, okay, you learn, okay, you need to read, okay, consider an infinite current surface in the Z0 plane if the sheet has uniform current density, must be uniform, okay, which is K. This is your current density K, Ky, Ay, shown in applying Imperial Law to rectangular closed path, okay, Imperial path, okay, so you need to make a Imperial path, okay. So now to evaluate the integral, we first need to have an idea of what hash is like. To achieve this, we regard the infinite sheet current comprising of filament DH or below the sheet due to a pair of filamentary current can be found using, okay, this one, these things that I talk about is this, okay. Okay, it comprises of small filaments DH, okay. Okay, and then as evident in figure 7.11b, okay, here. The resultants of the hash and has only an x component. Hash on one side of the sheet is the negative or on the other side. Okay, owing to the definition extend on the sheet. Okay, you can see here. Okay, before we proceed with the practice 7.5, you see we have two kinds of hash here. One is positive x, one is negative x. This is very logic. Okay, just like this. Okay, for example, like this, for this case, it's mentioned the surface current density is in z direction. You see this one is in z direction, your K. Okay, uniform current density, so your K. Okay, you see as what we see on the graph on this figure, okay, this one is specific for this condition, okay, we are not the same, okay, just but it's a bit similar, okay. This one is the sheet charge is lying like this, but for us it's lying like that, okay, but it's okay, just I want to show that what how they are similar. Okay, you can see here we have HO in the direction of positive unit vector x, this one negative HO in the direction of what, in the direction of negative vector x. So it's similar with this. You see we have z positive and we have negative z, okay, because one the other way up and the other one is the other way down, okay. Okay, and so we try to solve the equation, okay, we try to solve the problems now. Okay, and we also learn from page 304, because this is infinite case, right? So the general, okay, the general, you need to make specific into your solution problem. The hash is actually half of K uniform current density times your AN, okay, unit vector normal, okay, AN is unit vector normal directed from the sheet, from the current sheet to our sampling point, okay, to our, I usually put sampling point, point of interest is the same, okay? Point of interest. Okay, so now where is our point of interest for this equation? For this, our point of interest is here at the origin. Okay, our point of interest means we will evaluate the hash based on this. Okay, so first we have this equation, right? We have this equation. So we can solve directly. Let's say for hash, okay, at the point of interest 0, 0, 0, for infinite, half k an. Okay. So what is your k? K is given 50 z. Am I correct? And don't forget milli. Okay, milli means you will have some. You have milli here. Don't, so just put here in case you forget. Okay, milli, and then times with vector normal unit normal vector directed from the current sheet to our point of interest. So you know this one. What is your unit vector normal? Means your unit vector normal to the surface is in this direction. Okay, because it's at origin, so it is negative x. Am I correct? It is there, negative x, because towards, okay, your point of interest here. So you have this one is negative x. Okay. And then remember, this your friend is what? This is I'm sorry, there's a big mistake. I'm sorry. This one opposite is y, okay? I'm sorry, so sorry for that. So this is y. So this is y. Okay? It's y because couldn't be x, or x is here, is y. So half. Now you have this cross, okay? You have this cross. So what you know about the cross products? Okay. Okay, you have this is x, okay, this is z, okay, z, y, okay, z, y. So your cross product is actually in x direction, z, okay, because it's z, y here, so it is x, okay. So your resultant cross product is in x direction. Okay, this one just put here, okay, in case you guys forget later on. Okay, so actually, so it's actually 50 times what? This one is actually times 1, okay, just times 1, okay. Then because this resultants, okay, z cross product of negative y, okay, will result in x, okay. So you have 25 x meter, okay, ampere, milli per ampere per meter, okay. So that is your hash. So you will going to solve it the same for this one, okay. So I hope it's okay. You guys can see. Okay. Okay, now we go for the next question. Okay, we try. I try to see. Now we try the one at the back. Okay, the one at the back. I think it's more challenging. Okay, we try to see which one of this. Okay, you see page 340. Is about the Imperial Law is section 7.7.3, correct? Okay, so you can try a lot of exercise here. Okay, you can try, and if you have problem, inshallah, if I can help, I will help. Okay, so no problem. It's just the important thing is that you try. Okay, there's a lot of exercise, and actually this one, okay, I might take any of this as your quiz. Okay, I already spoiled my secret. Okay, So I might take some of them as your quiz. Maybe I just make differentiate, just change the equation, maybe do some changes, small changes as well. Okay, because I notice if I make question from scratch, just like question quiz 1, it'll be difficult for you guys to actually try to solve them. Okay. So I choose let's say this one. Okay, 7.22. Okay, 7.22. Let me try to read first. An infinite long cylindrical conductor of radius A is placed along the z-axis if the current density J is equal to J naught over rho Az, where J naught is constant. Find H everywhere. Okay, find H everywhere. You know, don't confuse. Sadiku always refer like this. Rho, this actually is a radius. Okay, this is actually radius. So we put, you see, from the solution you need to understand first. When it's mentioned infinite, then it can be used with the Imperial Law. Okay, but if it's not infinite, you cannot solve it. You cannot solve it using Imperial Law. And I told you, and I teach also, right, how sometimes the current loop finite, even though the current finite, but it can be treated as infinite if we have some assumption that make it valid. Okay, for example, the diameter is too small compared to the length, and something like that. Okay, assumption. Okay, so you need to be not only fixed with the word. Sometimes we didn't mention it is infinite in the test of final. Okay, we didn't mention, and you need to make assumption that it is infinite. Okay, so we go for this. Okay, this one, since it's mentioned here clearly infinite, clearly as this, so this one can be settled using Imperial Law. Okay, Imperial Law. Okay, we try to see first. An infinite long cylindrical conductor of radius A is placed along the x-axis. The same axis, make axis first. Okay, and it says infinite long cylindrical conductor of radius A. So we can make our cylindrical conductor first. Okay, and because it is infinite, okay, and then radius A is, okay, so we have, oh sorry, I don't have a good drawing scheme. Okay, and then we have radius of A. Okay, I put A here. Okay, not so much space. And then if the current density, okay, they give us the current density. Current density is J naught over R, okay, over Z, okay, where J naught is constant. Find H everywhere. Okay, so before we solve, let's recap. Okay, what is the step? Okay, first we need to know the coordinate, what we're going to use, which coordinate, and location of our H, and then we implement our circuit loop, Imperial loop. Then we solve that in using the equation. Okay, HDL I enclose, and also you can have extension. You can solve using this one. Okay, you have JLDL, JSDS, right? Okay. Okay. So clearly, when we solve this, we have two conditions now. We have R, we have 0, R less than A. Okay. Okay. So we implement our closed loop, closed current, okay, and close HDL equals to I enclosed, okay, equals to, because it's just like surface, so surface, you can see, right, where actually this you can imagine, because it's along the z-axis, so we try to look from upward. Okay, your view is from outward. For example, this is your eye. Okay, so the region is actually, when we try to make this into this view, okay, and you see current density, it shows positive z, so your current is moving upward. Okay, this one positive, so your current is moving upward. Okay, so when you see from above, it's actually going inside, going outside of the paper. Okay, going outside the paper is just like a dot going outside the paper. Okay, because you see this one, right? This one. Okay, this is your screw, right? So going out of the paper, so it's like a dot. Okay, if it's going in the paper, it's like this, you will see like a plus. Okay, so this one going out of the paper, so it's a dot. Okay, this is your cylindrical conductor. Okay, this just to show that the movement. Okay, and this one is doesn't mean that this is a line charge, a line current. Okay, I'm just showing the movement. Okay, the movement of the current. Okay, not doesn't mean it's a line charge. Okay, even though I'm constantly I draw it at z-axis. Okay, but just to show you the direction. So this one is going outside the paper, so you can see is this one, right? So we use this dot. So this is our loop now. We have our loop already. Okay, just like Gauss law. So we have the region now. So we have the region R A. Okay, and we have the region outside. Okay, this one is your A. Okay, okay, so okay, so you can see it is from above. So what is how are you going to solve this? Okay, is from above, so you actually what? Okay, first you see the DL first. Okay, the DL. Okay, so what is your DL? Your DL is actually 2 pi r. Okay, so this one, you know, this is a vector, time vector will result in scalar. So you should know actually later on your resultant is, this one is clearly we solve using cylindrical, right? So you need to make sure, you need to decide later on, decide now. Okay, actually this in direction of r, in direction of p, or in direction of z. Which one did you guys think? Okay, you see this, right? They are moving what? Moving up. Okay, let me show you guys. It's moving up, and the current, this is your field intensity. So if you see like this, okay, you see like this, right? So what is your field? What is the direction then? The direction is phi. Okay, so the direction is with respect to phi, because it's like this, and this is your with respect to phi. Okay, with respect to phi, and here when you see from above, it's just like this. Okay, your h. Okay, okay, I hope you guys understand. So that's why h here is actually in terms of phi for this case. Okay, and then you need, and then the DL. Okay, the DL is 2 pi r. Okay, and then I enclosed here, you solve using, you extend just now, right? We have another equation just now, GS just like Gauss law. Okay, Gauss law, what you know, rho v dv equals to q enclosed equals to what, right? D. Okay, So h2 pi r, okay, then you have double integral because it's a surface, okay, you have double integral. Then they give us here, okay, they give us this j naught over r, okay, over r, and in z direction, okay, and after that it's a dot. So dot means you need to have surface the same direction as this one, otherwise it's zero, because for scalar, okay, scalar, if you have similar direction, then you get a non-zero for same direction, okay. But for the for you will get zero if it's like orthogonal, okay. So this one, if this is z, for it to be non-zero, it should have another z component as well here, okay, z component. So z component, okay. So this one is given, okay. Now we need to decide our ds. We need to decide our ds, okay. So how is it, okay? Any idea? Okay, for it to have z component, okay, for it to have a z component as the because this is your z, okay. So what you have, okay, what we learned from the previous okay, I try to relate, okay, so that you guys see that actually this one is interrelated, in case you guys didn't hopefully, I hope you guys don't forget, but I want to show from the, you know, this why EMT is interrelated. You always need to master the previous chapter because it will be used for the later on chapters, okay. So if it's okay, page 33, okay, page 33, okay, here. So for it to have a z direction, you need z direction, so we're using this r d phi dr, okay, r d phi dr. So it's actually r d phi, okay, and dr. So where is that actually? Where is this guy actually? Where is this r d phi dr? Okay, r d phi, okay, r d phi is here. This is r d phi, your kind of length here, okay. And then where is dr? Dr is here. So where is it? Means that it is, because it's in z direction, okay. So the surface actually that you trying to solve is this, okay. That's why you see from above, right? This is this, and this is the one outside. I just make a color so that you guys cannot see, okay. Is it clear? Okay, so we solve accordingly, okay. We just solve this z because it's dot will become scalar later on. So you see, you need to have a range of r, then you have a range of r and also phi. So what is your phi? Phi is nothing because it's closed, right? Closed loop, so 0 until 2 pi. And how about r? R, of course, from 0 and up until value of what? Until value of r, not a, okay, because it can change, okay. Until value of r, okay. Then you have j naught over r r d phi dr, okay. You can see this one cancel out, right? cancel out. So you will have, just to make it very fast, you have HP. So this one will be what? J naught. This is constant. This one cancel out. So you have another R again. Okay. And d phi is 2 pi. So 2 pi. Okay. As easy as that. So you have this. Okay. And for the regions, we see another region. Okay. So this one you can, if you want to solve for the hash, right? If you want to solve for the hash, this, okay. So now we go for the other region. Where's my other pen? Okay. Now if you want to solve for the regions, okay, for the, I hope you guys can see, okay, because I'm sitting right now, so I didn't see. I hope. Okay. Okay, now we have, you need to solve for another region now, which is what? Which is R greater than A. Okay. Similarly, okay, you also the same. You hash DL. Okay, it's not a closed loop. Okay, here you solve using HDL because our loop is here. Okay, HDL, and then we have JDS. Okay, the same, and the same also integral results. Okay, not the same. I mean a bit similar. So 0 until 2 pi, and your R limit is changing now. Okay, your R limit is changing now, means you have R equals to 0 until R equals to A. Okay, just like Gauss law, this part is vary, and this part is fixed in terms of the value. Okay, so you have just use the same J naught over R d phi dr. Okay, so the same is H two pi R equals to J naught 2 pi what? 2 pi A now. Okay, 2 pi A. Okay, oh, I'm sorry, there's a bit wrong here. Okay, this one I forget to divide it. Okay, so it's a H so J R, this one 2 pi, you put 2 pi R, so you left with, I'm sorry for that just now. Okay, I forget to, so you end up as H equals to J naught. Okay, here for this region. Okay, I'm sorry, I forget to divide it. Okay, so you have, proceed with this one. So you have H 2 pi R J naught 2 pi A, then you have your H J naught 2 pi A over 2 pi R. Okay, 2 pi R. So what? Cancel out. Cancel out. Then you have H is H equals to J naught A over R. Okay, so then you will have, depending on your location of interest at which, so you have different value. Okay, so your H phi, okay, H phi in terms of magnitude. Okay, in terms of magnitude. Okay, in terms of magnitude, so you have J naught for region of R between 0 to A, and for R greater than A, it is actually J naught over A over R. Okay, see this? I try to zoom out so that you guys can see it more clearly. Okay, So this is the total so this is the total solution. Okay, so with that we end our Imperial Circuitry Law lecture. Okay, and we will continue later on. Okay, now is 2:40 a.m. so it's exactly 1 hour. Okay, see you guys and good day.